Hey CW Apes, Mr. Kennedy here, and today I have a special video for you just on ozone. You need to be familiar with ozone for a couple of reasons. One, it's a greenhouse gas, and two, it plays a really important role in our air quality and protecting us from stuff like ultraviolet radiation. So let's dig in. Let's learn about ozone. To start things off, let's deal with this simple question. What is it? Ozone is the 3 oxygen atom molecule that we find in the stratosphere. There in the stratosphere, it protects life on Earth from harmful radiation like UVC and UVB radiation. If that stuff gets down to ground level, it could cause cancer, it could damage your retina, it could damage crops. This is bad stuff. So we need something like ozone, O3, a molecule made of 3 oxygen atoms bound together to block that and protect us. Now, when you think about this ozone in the stratosphere, the layer that it exists in, we call the ozone layer. And if you were to just kind of like measure it out in terms of its overall thickness with regard to the other gases in the layer that it exists in, like the ozone layer is about 3 millimeters thick, sitting right between the stratosphere and the troposphere. That's a super tiny layer of gas, right? Just to kind of give you perspective. Like it's super tiny, right? So like we should be careful and be like cognizant of this layer and protect it. So when you think about the total of 10 kilometers of troposphere to anywhere from 10 to 50 kilometers of stratosphere, like the ozone layer is about 20 to 30 kilometers in its like thickness, which is the equivalent of about 3 millimeters, okay, to scale. So how is stratospheric ozone formed? This, ladies and gentlemen, is a reaction that you need to know. You need to memorize it. Write it down. Tattoo to your brain. Like you got to know it. So how do we form ozone? Well, it's right here. We take oxygen gas, and when it is struck by UV rays, it breaks apart into single oxygen atoms. We call that singlet oxygen. When those singlet oxygens bounce around in the atmosphere, they can either find each other again and make O2 gas, or sometimes they will find O2 gas that already exists, jump on with that, and then we've got O3. That's how it's formed in the stratosphere. Now, how does ozone absorb UV light? Well, just the same as what you just saw here. O3, when struck by UVC, will split into oxygen gas and then singlet oxygen. That free oxygen atom can then combine to form ozone again. So it's kind of like ozone is constantly being made and broken, made and broken, made and broken. And that's how it shields us from that UVC. Ozone protects us from harmful radiation by taking the blow for us instead of like allowing our genetic material in our cells to take the blow. Now, we did for a long time hear a lot about an ozone hole on our planet. In the 1970s, ozone loss was detected over Antarctica. There was a thinning in the ozone layer of up to 70%, and it kind of like, varied by season. It was much worse as we kind of like came into the spring months. There was less thinning over the Arctic. The thinning developed rapidly, and basically it would have been discovered earlier if the computer hadn't disregarded such a quick change, when the data was first collected. This is what the ozone hole looked like basically from 1979 up through 1989. That big black dot that you see there, like that's Antarctica, and the progressive damage to the ozone hole is all around it. Okay, so where did this like ozone hole come from? Like what's the cause? Well, it's a fluorocarbon that has chlorine associated with it. It's called chlorofluorocarbons, and it was once used, as I mentioned a while ago in this video, in like propellants. It was used for things like aerosols in deodorants and hairspray. It was used in refrigerators. It was used in like blowing agents to make styrofoam cups, cleaning solvents, You know, all kinds of different things chlorofluorocarbons were used for because it was stable and it was considered safe, right? CFCs are colorless, odorless, and so stable that, yeah, once they're released into the atmosphere, good luck getting them out. And the problem is the chlorine really, really likes that ozone. And so it gets up into the atmosphere and it attacks that ozone and it holds that oxygen and prevents it from going through that cycle of becoming O2 and singlet oxygen and then reforming ozone gas. That's a bad thing, right? So then your ozone that's bombarded by UV rays, like if there's chlorine around, like it just absorbs all this singlet oxygen and there's no singlet oxygen anymore then to combine with O2 to make O3, and there you get the hole. All right. Um, Basically, we also have the ozone hole that is increased by using bromine and halons and fire extinguishers and pesticides, along with the chlorofluorocarbons. So, how do CFCs destroy ozone? Here's the chemical equation for it. Chlorine acts as a catalyst, and it gets in there, and like I said, it binds up that singlet oxygen. Each chlorine atom can last 65 to 135 years and can convert up to 100,000 O3 molecules to O2 before it finally combines with hydrogen to make hydrochloric acid and then rain down on us like acid rain. Okay? How does CFCs contribute to ozone depletion? Well, the CFCs, like they put the chlorine in the atmosphere. So here we have the chlorine plus the O3, right? Taking up that singlet oxygen as illustrated on that previous slide. Why is ozone thinning seasonal? I mentioned a while ago it was kind of like worse in the spring months and stuff like that. Well, in the Antarctic during June, a polar vortex of icy clouds provides sites for the CFCs to react and produce our chlorine atoms, but they stay attached to these icy clouds until spring. In spring, the ice crystals melt. That releases the chlorine atoms into the air, and that's when the ozone takes the hit. The largest thinning in the Antarctic occurs during the spring months. What happens to us? Well, unfortunately, it's not pretty. When we get increased exposure to UVB and UVC, it damages the retina. It can lead to increased incidences of blindness and cataracts, skin mutations, skin cancer, crop damage. The list goes on and on and on. Mutations leading to cancer, it happens in human skin, but it can also happen in lower life forms. Amphibians are more susceptible to harmful UV because their eggs are transparent. So we could lose amphibian life as a result of exposure to ultraviolet radiation. The average increases in exposure to harmful ultraviolet radiation per latitude are listed for you here. And what you can see is the exposure rates go up dramatically as you get closer towards these hole locations in Antarctica and the Arctic. So what are we doing about it? Well, we're trying to protect the ozone layer. In 1978, the U.S. banned the use of CFCs. In 1987, the Montreal Protocol was passed, which we talked about in a previous video. Initially, 24 nations agreed to cut CFC emissions by 50% between 1989 and 2000. Now, that number is up to 197 countries that have signed a goal to completely phase out the CFC use. And while that sounds great, let me just put it this way. There's more than 197 countries that are out there, right? So there are still some places that you can find that are still using CFCs, and hopefully the levels that are being released into the atmosphere are much smaller as a result of these activities. I can tell you this, the good news is chlorine levels have already begun to decrease, and as a result of this action, our ozone holes are getting smaller. The thought is that by maybe sometime between 2045 and 2049, like there might not be an ozone hole at all. All right, ladies and gents, so that's the long, the short, and everything there is to know about ozone. I hope this has been educational for you, and I will see you next time.